I'm Lukas Fittl, founder and CEO of PG Analyze. We're going to talk about how to optimize slow queries in Postgres. Specifically, when you have an explain analyze output and you don't know how to interpret it, I'm going to give you a few tips and tricks and a better mental model for working with slow queries in Postgres and how to fix them. All right, let's dive in. So there's 5 things we're going to talk about today. First, how to debug why a query is slow. Second, how we can benchmark queries with explain analyze with the buffers option. Third, how planner costing works and why it really can never be perfect. Fourth, we talk about join order and how parameterized index can greatly affect query plans. And last, we'll talk a little bit about how we can guide the planner to the right plan. So generally, I think it's important to have a good sense for how you go about debugging, right? Like what a good debug loop is that you can think of. And usually I start in debugging when I'm saying, well, is a query always slow or is it just sometimes slow? Typically, here we have a query that has 1.4 seconds of average execution time, but the outlier took 14.6 seconds, right? So this is usually a good starting point saying, well, why did it take 14.6 seconds in that one case? Oftentimes, I/O time can be the problem. So I/O time might be, a particular node just taking either loading more data or maybe the disk is overloaded, and that greatly influences, of course, the total runtime of the query. And unfortunately, especially in the cloud, I/O latency can be pretty bad. Postgres 18, which is the upcoming Postgres release, will make some of these things better. But for now, on most production systems, we'll have really inefficient I/O on some of these cloud provider network storage options. Also, sometimes what we see is not necessarily I/O being the problem, but the plan having changed, right? So query might have a good query plan and a bad query plan. For example, maybe an analyze ran recently and changed the internal statistics, or other things caused the plan to change. And so really where we're starting with, we say, well, we had a slow query. It's slow. What can we do? So we start a benchmark query with explain analyze, which is basically just put explain analyze in front of the query. We form a thesis on what to change based on that explain analyze. Then we try out a change, which might be rewriting the query or other optimizations. And then hopefully, what we're trying to get to is that we actually made the query fast. And then we figure out a way to make that change permanent. Right? This is a loop that people go through day to day all the time with Postgres, right? As they're debugging slow queries. So this shouldn't come as a surprise to you if you've had a slow query in your life before. But what I want to give you is basically better tools of working in each of those steps. So just in case you're not familiar, I want to repeat maybe the most important things about how to interpret explain analyze. So explain analyze, right? We just, either put explain without the analyze in front of a query, explain analyze, or then explain analyze buffers. In the upcoming Postgres 18 release, buffers will be the default. So if you just run explain analyze without specifying buffers, it will automatically be set. You can do buffers off if you want to turn it off. Now, an explain output without the analyze just gives us the query plan that Postgres wants to use, but it doesn't tell us anything about, the actual execution statistics. For that, we have to add explain analyze, which in this case shows us that the query executed in 307 milliseconds of runtime. It also tells us things like, did a particular plan node perform, worse than expected? Did it remove a lot of information after, for example, scanning the table and such? And then when we add the buffers option, or again, if you're in Postgres 18, then you'll actually get information like I/O timings and how much data was read. This is really important because it helps you understand whether the slowness of the query comes from the amount of data it's working with, that it had to load from disk, if the data was in the cache, and such, right? So it's really important information for debugging. Now, when we see buffers, what we mean with a buffer is an 8 kilobyte buffer page. Basically, the internal storage of Postgres is structured this way. So each time you load data, even if you load just a single row, you'll have to load a full 8 kilobytes of buffer page from the disk or from the memory. Now, the number of how many rows you have per page is greatly influenced by table bloat. So if you have a lot of dead rows and then your table bloats and you have a lot of empty space in your table, that greatly influences how effective your scans are. And so it is important to watch these buffer counts if they're unexpectedly high. Also, the other thing to note is if you see a hit counter in the buffer's output, that means it's a cache hit. That's generally a good thing, but it can be confusing because the problem is if you have a nested loop, the loop loops over the same basically data over and over again. What can happen is that it basically double counts the same buffer block. So in this case, for example, it might have been that there were only 12 buffers uniquely loaded, but 1,200 buffer accesses occurred. And so you've got to interpret these hit counters when you see them. The other thing to know with explain analyze is that it has overhead. So when you run a query without explain analyze, and it's a query that doesn't work with a lot of rows, usually the measurements are pretty similar, right? However, once you have a query that's very slow, in this case, the query just measured from the client side takes 340 milliseconds. But if we measure the query with explain, analyze in the picture without timing, which means no per node timing information, it's similar, right? It's 404 milliseconds. So we added a little bit of overhead here. But where it gets really bad is if you have timing on and the buffers option on, then Postgres basically measures each repeated access to the plan node, and that just takes a lot of time. And so when you benchmark, explain, analyze will give you the insights into what's going on, but you should always run it without the explain, analyze also to get the true performance, basically, without the overhead of measuring this. Now let's talk a little bit about planner costing. So planner costing is basically the mechanism the planner uses internally to decide which query plan to use. So, you know, core mechanism here, right, is like we looked at, we have a bad query plan, we found it, explain, analyze. Now let's form a thesis on what to change. That thesis has to interact with how the planner, comes up with a plan. And so, as Tom Lane said in the presentation many years ago, ultimately the planner's task is fuzzy, right? So there can be many valid plans for the same query, but it's not always clear which one is the best query plan. And so basically the planner has to find a good query plan, but it also shouldn't spend too much time or memory finding it. And it also needs to support the extensible aspects of Postgres, right? And especially that last point means sometimes, Postgres has to do more work to figure out which data types, are being used and such, which index access methods exist. And so some limitations exist because the planner is extensible, but then also, wants to consume finite CPU and memory. So most important thing to know is the planner does not find all possible plans. It actually discards plans that look bad pretty quickly. Also, it doesn't change plans when expectations don't hold true. So if your row count is off, then it doesn't fix that. It doesn't rerun. And also, it doesn't know if past executions of the same query had a bad plan that performed badly. It will happily keep doing the same slow query. So really, cost estimation is how the planner makes decisions. Ultimately, garbage in, garbage out applies here, as Tom said in the mailing list comment some time ago. So basically, if you put bad data into the query planner, as in bad statistics, you'll get a bad query plan. Now, quick information here is we can look at the cost on each of these plan nodes. The cost basically has a startup cost component, which is the first row you're fetching, and the total cost is if you fetched all the rows with that particular method. Right? In this case, the index scan, if we basically scanned for all those rows. Now here, we estimated that there's 10,000 rows being fetched, which is the output of that plan node. Then we also, the planner also estimates how wide each of these rows is. But what is cost really? Cost is not really a specific unit. It's more a currency that the planner uses when it does its cost-based search, right? So it doesn't you could argue that maybe what it means is the cost of sequential scan. So one of the core things, if you look at how Postgres internally costs a sequential scan on a table, it basically multiplies the sequential page cost, which is set to 1 by default, with the number of pages you're looking for. So if you have a table that has 8,000 pages, the sequential scan cost will be 8,000 roughly. So you could say that that base sequential scan cost basically is what all the other costs are based on. Right? Most importantly, what's the cost of an index scan? Well, the cost of an index scan is dependent on which index access method you're using. So if you use a B-tree index, it's going to be different than if you use a hash or Brin index. And because, again, Postgres is extensible, this passes down to the particular index access method. For example, in the case of a B-tree index, we have the BT cost estimate function. That function ultimately tries to figure out how selective is the part you're looking for in the index with, doing a selectivity calculation, and then it multiplies that with the number of tuples, and then it factors in the regular costs. Now, this function here, this clause list selectivity function, is one of the key facts that will impact your query plan's performance, or the query plan's quality, rather. So this here basically works from limited information, where it's like you're looking for this, we have these filters on this table, and you're trying to say, is this, likely to be found, right? Like, am I looking for something that's very unique, or am I looking for something that's very common in a table? And that then drives how selective your query is, how selective your search is, basically in the table or the index. Now, this, then drives the cost, right? Because the cost basically multiplies with that selectivity number. So, for example, the way we can see the selectivity number is kind of indirect, because it's the total number of rows times the selectivity, right? That's the row number you see in the plan. The most typical issue why you get bad row estimates is because clauses are not independent. What that means is if I'm saying A is 1, B is 1, C is 1, D is 1, and E is 1, then basically if all the A that are 1 also have B1, or there are no C1s that have D1, right? So basically if there's dependencies between those different conditions, Postgres does not know that by default. And so because of that, what Postgres will do is will think if you add more conditions, things become more specific, so it will underestimate the rows. Now, we can improve this by using the create statistics command. So the create statistics command basically tracks additional information, specifically this dependency between columns, that lets us then improve the situation. Another problem on selectivity, though, is join estimates. So join estimates are really complicated and often wrong. I won't have enough time in today's talk to really go through all the details here, but suffice to say, if you want to look for this, look at the Postgres source. One of the things to know about joins is that the most common value lists are being used for that. So Postgres, when it does an analyze run, will collect the most common values in a table, and then if those basically align with, the two tables being joined, that is used to drive, some of the join estimates. But one of the ways you can improve, the quality basically of a join selectivity estimate is you can increase what's called the statistics target. That then increases the number of most common values that are collected, and that way you might get a better estimate of how many rows get returned by a join node. Now let's talk about joins in a little bit more detail. So ultimately, when we talk about joins, we have to think about two tables, in this case, A and B being joined. So here we see a sequential scan on A, index scan on B, and we join those two together in a nested loop join. Oftentimes, joins are more complicated, right? So in this case, maybe we join the result of that A and B join with another table C, and then it becomes, ABC as a join. Um, this here, is what we call the join order. So in this case, the join order is ABC. We can also turn this around. So maybe, just to illustrate the difference here, maybe the join on C happens earlier and then the join on B happens last. And so the join order becomes ACB. This performs differently, right? Because you basically filter things out earlier or later, depending on the join order. This, ultimately drives a couple of things. So for example, join order can influence which scan methods get used. We'll talk about parameterized index scans in a moment. Join order itself also can, just by virtue of eliminating information earlier or later, influence the performance of a query plan. And then join methods, like whether you have a nested loop join, a hash join, or a merge join, also again, our choice the planner makes and are influenced by the join order and the scan methods, right? So all of these are kind of interdependent with each other. One of the things you can do, and we've done some kind of prototyping around this ourselves at PG Analyze, is you can detect the join order in captured explains. So imagine you use auto explain, you're looking at all the slow execution outliers. You can actually analyze which join order is being used by your queries. And so the one thing that surprised me when we did this is that it actually does change for the same query, right? So you might think Postgres chooses one join order and keeps it, but the reality is that depending on the input parameters, Postgres will use different join orders because it thinks that maybe, the data being returned from one part of the join is going to be less in one case. And so this, like, mapping this out can be useful for, highly frequent, changing queries, basically. The other thing to know about is what we, or to think about is how can we filter on particular parts, right? So here in this query, we have a sequential scan, and you can see that, in this case, we have a hash join. And so the hash join is the one that basically does the, merging of the two, and the filtering happens like on T2. There's no filtering when we load the data. It's really when we join the data that we filter. Now, the most important thing to think about here is that we might have what we call a parameterized index scan, where basically here's a nested loop, and parameterized index scans require nested loops. And basically what happens is that you first load the data from the one table, and then each of the result outputs from, in this case, T1, gets passed to the index scan on the second table. And so this means that, for example, when our query says, load from table 1 and also load from table 2, and then match up, the table 1 ID with the table 2 ID, Postgres cannot, doesn't know what the value is it's searching for. And so the choices you have here are basically very limited, right? But if you have an index, in this case on T1 ID, on that second table that you want to use, you have to first know the values looking for. And so it's going to get the values first from the first table and then put them into the second table to basically locate the actual rows. Another way of putting this, right, is like these are basically the same query, just two different plans. Either you have a hash join, and then if you have no index scan that's usable without the value being known, then you basically either have to hash join with a sequential scan on the left side here, or you have a nested loop join with an index scan on the right side. And the index scan uses this parameterized index scan, parameterized because it inputs the values from the other table. Parameterized index scans must be on the inner side of the nested loop, so this is where the join order comes back, right? If we have bad join order, we're not going to get this. Now let's think a little bit more about how we can guide the planner to the right plan. So when we think about query being slow, right? And we formed a thesis, we understood kind of the costing, what's going on, the join order, like we looked at all these attributes. Now we're trying to say, what can we try to improve this, right? How can we actually get to a better plan? One of the things I like to do is trying to force a good plan, and then seeing why Postgres chose a bad plan. So one way you can think about this is you have this query, right? The planner produces, for a particular value, a good plan. But then there's also always a bad plan, ultimately, right? The bad plan has a cost. And what you're hoping for with a cost-based, estimate by a planner is that the estimate models the reality, meaning the bad plan doesn't get chosen because it has a higher cost. Now, what can happen, right, is like you might have different input values. So in this case, it might have, different object that you were looking for. And so the bad plan gets chosen because the cost is different, right? And so even though basically it's the bad plan because of the input value having different selectivity, we're getting, the bad plan because there's lower cost, right? So again, this case, bad plan has cost 300, the good plan has cost 500. Postgres doesn't know ahead of time which plan is going to be better, and so it chooses the worst plan, basically. So one of the things we can do to improve the situation is we can turn off planner features. So planner features are, for example, sequential scans. So let's say we get a bad plan that's a sequential scan and a good plan that's an index scan. Well, we can say set enable sec scan off, which means Postgres basically makes the sequential scan extremely expensive in old versions, or in Postgres 18, this is changed with an explicit disabled plan notes setting. So it's just visualized a little bit differently. But the fact remains the same. If the sequential scan is the only viable option, it will still give you a sequential scan. It's just extremely unlikely to do that if there's any other way to basically give you a query plan. Now, in this case, what we see, right, is like we get the good plan, and most importantly, we know that the good plan has a cost of 500. So once we have the right plan, we can then look at the right plan with the wrong costs, and we can find out where our misestimate is happening. For example, another thing you can try is if you're seeing your hash or merge join being used, but you wanted to use nested loop, you could turn off merge and hash joins and see what the nested loop plan looks like. Now, sometimes this works really well, and sometimes it doesn't work well. And where it doesn't work well is when you have complex queries where maybe you want to turn off nested loops for one part of the query plan, but you want to keep nested loops for another part of the query plan. And so for this, we can use PG hint plan. So PG hint plan basically lets us specify specific parts of the query to be done differently. So here, for example, we have a bad plan with a particular join order that we don't think is good. And so we can, we also know that, there's another plan that worked better. And so what we can do is when we look at the good plan, basically we come up with an idea of how exactly to, force the order. And in PG hint plan, look it up. It's going to take a long time to explain in all the details, but basically PG hint plan has things like for this table, use this index. For join these other tables, use this order, right? So it's basically prescriptive about how the planner should do things. And so in this case, now we know that, the good plan, for example, had a cost of 1.4 million. The bad plan, in this case, without the memorize function, had 14 million costs. So that actually would have been fine. It would have been worse. But because of the memorize feature in Postgres, the bad plan was chosen because the bad plan had a cost of 900,000 instead of 1.4 billion, right? And so now you know that, okay, what happened was memorize, made that difference basically between those plans. So to summarize, there's basically 6 ways to guide the Postgres planner that I can think of right now that I would like to give you on your journey. First of all, if you have simple scan selectivity issues, right? So if you have a problem where the Postgres planner, gives you the wrong row count, look into using create statistics. Create statistics collects, additional information. This doesn't work for cross-table situations, but it works well if you have these functional dependency issues. If you have join selectivity problems, increase your statistics target to increase the number of most common values to help the join, improve selectivity. Sometimes with join selectivity, you can also force materialization, which is another technique I sometimes like to use. Reviewing cost settings can help, right? So as mentioned, these, Postgres settings like random page cost, sequential scan cost, they do significantly influence what the planner does. And so again, one common problem might be that, for example, random page cost is still set to 4 by default. And so random page cost being high means that you get certain like indexes being used versus others. Like there's lots of details to this, but basically reviewing those settings and sometimes lowering random page cost in particular can make sense. Um, Sometimes, and we didn't talk much about this today, but it makes sense to understand what particular biases the planner has. So one common situation I've encountered is order by limit, and so sometimes that causes a bad query plan. And so creating multi-column indexes in the right way is a good thing to think about. As mentioned, materialization is a way to fix things. So if you don't want to use a planner hint, which you shouldn't, if you can avoid it, using the materialized keywords for CTEs lets you control which part gets loaded first in Postgres. So that's kind of a neat hack sometimes. And then one trick that I would give, on a journey for anybody who runs a multi-tenant app, where you have, different customers, but they're all in the same, database, right? So you have a shared kind of table for all the customers. It makes sense to basically give more of your tables a customer ID identifier or something that basically identifies the tenant, and then adding explicit clauses and duplicative clauses to your query plans. That seems a little bit nonsensical, but the reason you do it is that the planner basically has more choice in terms of query plans because it's not forced to use a parameterized index scan. And as a, kind of overarching principle, I would say choosing better statistics or rewriting queries is always better than choosing planner hints, right? So planner hints really should be a method of last resort. PG hint plan works. Some people use it in production, but it is not efficient. Like it causes overhead on each query we're using it. And so I would only use it if you have no other way of fixing a query. And that's, that's basically it, right? Like so query plan like optimization isn't magic necessarily, right? Like it is in a sense a deterministic process that Postgres does. And so I would really encourage you to basically experiment, try to get a better mental model of how Postgres comes up with these query plans. And then if you're interested, PGAnalyze helps you make these things easier. But I do think that there's, a lot of things you can do just with a pSQL shell or, pgadmin and just running explain and having a good mental model of how row estimations work. I'm looking forward to, talking more about this. If you want to reach out to me, feel free to email me, lucas@pganalyze.com. I'm always happy to talk about how to optimize Postgres queries. Thank you.